So practice test, just want to kind of go through these, setting them up for you quick, for you to watch through. You can solve them. I'm not going to solve them necessarily to a numerical answer, but get you like to the step C part. So remember equilibrium problems, we're worried about X and Y. We're asking you for T2 and T1. Those are the answers we want. All right, so sorry about that. Little phone call, important phone call. But so we want to find those two tensions, right? T2 is really easy because it's horizontal, which means there is no vertical, right? We like horizontal and vertical. T2 is horizontal. Awesome. That means less work for us. T1, we need to find an X and a Y, right? So we need to find the horizontals and verticals. So I can redraw this free body diagram, remember, like this. We've got MG, we've got T2 pulling this way, we've got Y1, which is that component, vertical. We've got X1, which is this component horizontal. Remember that whole thing we talked about? The sum of X plus Y is T, right? We've been over that. We have to put that frame of reference into our brain. When we're doing vectors, vector X plus vector Y is vector T. Okay, it makes the triangle. So since this thing is at static equilibrium, which means it's not moving, we know that those have to be equal. And we know that these have to be equal. The X's and the Y's have to cancel out. Y1 equals mg. Okay? And so it basically, when we do the static equilibrium, it becomes a trig problem. We've got our triangle. Remember, T2 is really easy. Okay? We don't worry about that. But the triangle over here, the hypotenuse is T1. That's the answer we want. Okay? We know that Y1 equals mg, which we know. Okay? We know the angle. And we want T2. We also need T2, but it just so happens that they're equal, right? So essentially, this is my triangle, right? I can replace the Y with mg. I can replace the X with T2. And the answers I need are these two. I know mg, right? 10 times 10. And I know the angle. So you're doing trig. Okay, you're simply doing trig. Now, the sticky part of this is we generally, in the past, we've done trig. We've given you the hypotenuse and are finding the sides, right? Mg sine theta, mg cosine theta stuff. In this one, and this is one of those really simple math things that we get confused on at times. Let's do the sine, right? Sine of 40, right? Or sine of theta. Let's just back it up a little bit. Sine of theta equals the opposite over the hypotenuse, right? How do I solve for the hypotenuse? We can't just say mg sine theta. Okay, it's not the same. That's that gut instinct from what we were doing before. We can't just say that because that's in the denominator. So I have to multiply by T1 and divide by sine theta. We've flipped these essentially. So T1 equals mg divided by sine theta. So just be careful about that. All right? So I'm going to pause while I erase this. I don't want to waste any time on this video because I only have 15 minutes. So I'll be back in a second. All right, problem 2, Atwood sliders. Okay, this is a simple. Remember, this is as simple as we can get, frictionless. Right? We've got two masses, the suspended one and the flat one, and we always start with the free body diagram. Now, remember, this one is always exactly the same. Always. Okay, we've got mg pulling down, ft pulling up. The net force equation, net is ma, right, equals, we like to call that positive because that's the direction it's moving, m2g minus ft, right? That will always and forever for a hanging mass, a suspended mass, be the same. Hopefully by now that's starting to beat its way in your brain, right? All right, and don't these points ignore them. These are some old problems that we used to that I dug up from the CIS vault, so don't pay too much attention to this. For this one, we've got M1G pointing down. Remember, M1 and M2 are different. We've got normal force up, and we've got tension force this way. No friction. right? A lot of people yesterday were putting an FF arrow in there. There isn't any friction. It says frictionless. Okay, so what's the net force here? Well, these two cancel out because we're on flat ground, right? So the net force here, M1A, is going to equal just Ft. So I've got my two equations. Remember the Atwood machine, there's always two net force equations that we merge together. Okay, so merge them together. That's what's happening down here. Sub this in for Ft, right? We get M2A equals M2G minus M1A. Get the A's together. M2A plus M1A equals M2G. Factor out the A. Remember, this is the part I told you about before. At some point, we're going to divide by the whole mass. This right here will change. As the problem gets more elaborate, there's going to be more crap on here, right? But for now, we're going to divide by the total mass. A equals M2G over total mass, M1 plus M2. Right? This right here is going to become more elaborate as the problem gets more elaborate. This is a simple one. That's fine. So here's my expression for acceleration, my formula. Okay? You can plug in and solve given the masses. M2 is 3, right? M1 equals 2 kilograms. M2 equals 3 kilograms. You can solve that. That's on you. Now, part C, is the tension in the string greater than, less than, or equal to the weight of the block 2 and y? Remember, first off, the thing that I answered a couple questions on yesterday, these FTs are the same. There's not a different tension here than there is there. Tension in a rope chain cable is the same throughout. Okay, so this is just a simple, and there's no math, there's no expression, this is just looking at the picture. Okay, now we know that if this object, we know that it's accelerating, right? I believe the answer was something like 6. I don't have the key in front of me right now, but I think that's the answer. We know it's accelerating that way at 6. Well, we know, according to Newton, that if there is an acceleration, there must be a net force, right? And what does that tell me? Well, net force tells me that this side wins. If there's a net force down, that means the down must be bigger than the up, right? Just like in the tug of war. Whatever direction the rope goes, there's a greater force. Same thing, okay? So that's simple answer there. There's no math involved. And then part D, suppose that it hits friction. What happens to the tension? Don't think so hard on that one either. If the sliding mass encounters friction, what's going to happen to the tension force? Okay, don't think so hard. The tension force is going to go up, right? It's going to cause, getting in deeper into the physics, what's going to happen if that happens? Well, that's going to cause an acceleration this way, right? Which means there's going to be an increase in that resistance force acting against that guy. So there will be an increase in friction if it or increase in tension if it encounters friction. Okay? All right. And last but not least, the multiple choice. Okay, person gives a box a shove, so it slides up a ramp, then reverses the slide down. The force of friction is what? No math on this one, right? There isn't really much math on, oh, there's on the last one. Friction always acts opposite of motion, right? So as the box slides up the ramp, as the box slides up, friction is going to be opposite. As the block slides down the ramp, friction is going to be opposite, right? So friction always opposes motion. Now this one is, I believe, an attempt to mimic the question. If I said the force of, or the direction of acceleration, that's always going to be down, right? Because of gravity. So it's kind of a trick question because it's simulating one you've seen before. Sorry, my finger just hit that. Apologize. Okay. The next one. Block at the right sits and stays in rest. So it's at rest, which means it's stationary, right? Which means that when I add up the mg, the ff, and the fn, it's going to make a nice pretty triangle, right? So the question says the forces that the slide exerts on the block. Those forces are these two. when I add those two together, right now they're tail to tail. And friction, weight comes from the earth, right? We don't care about that. So when I add these two together, the resultant will be approximately straight up, right? Number 3, P and Q are on a perfectly smooth horizontal surface connected by a light cord, yada, 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 right? So think of this. F, right? This guy right here is pulling both blocks, right? So where is the force going to be greater? Here or here? Okay? If you're pulling both blocks, your force is going to be greater. That's going to be the bigger one, right? So between P and Q is going to be small. Is it going to be 0? No, because there's still going to be a tension force, right? So don't think so. Number 4, I'll roll this up a little bit. Number 4, this is kind of covering this. This is a topic that's kind of an auxiliary topic, related a little bit to, hey, that work fits pretty good. Sorry, my fat fingers, fat hands. The whole machines pulley thing, we don't spend a lot of time on this, so I kind of like having this in here so we can address it. These are TAs, right? You've seen this. This is TC, and this is TB, right? And we want to know which is the biggest. Well, we know for a fact that TC is holding up M, right? It's holding up the weight of the mass, or the weight of that mass, weight of that block. Okay. Now, this one here he's pulling down, but we can see TA. There's 2 ropes holding up M, right? So we know that TA, or 2 ropes holding up this down here. So we know that TA is going to be equivalent to TC divided by 2, right? So just looking at A and C, which is bigger? Obviously C is bigger, right? So C is bigger than A. We know that just looking at it because there's 2 A's holding up C. Well, then we get to B at the top. B is holding up not only TC, but also this. We're pulling down on this whole system, aren't we? To hold this thing up, you're pulling down on it. So it's not only holding up TC, but it's also holding up TA. Right? And so the reason why when you use a block and tackle, it saves you, it's easier to lift heavy weights, is because we're splitting that weight. I'm only pulling half of the total weight. If I added more pulleys with more supporting ropes, I would be, if there was 4 ropes supporting it instead of just 2 here, if there was 4, I'd be pulling 1/4 of the weight, and so on and so forth. So that's how that works. But in our answer, obviously, TB is the biggest, TC is the middle, and TA is the smallest, right? So you guys can actually answer that. And the last one, Hans pushes a 10-kilogram wood box across the floor to steady speed. Steady speed means acceleration of 0. What does that tell me about the forces? It means the forces all cancel out. This is an equilibrium problem, right? He's a steady speed, but there's no acceleration. So we know that all the forces have to cancel, right? So the push force has to equal the friction force, right? Does that make sense? So our job is to calculate friction. I'm running a little short on time here, so I'm going to talk fast through this. FF equals mu Fn, right? Well, we know 2 things. We are moving, so this is kinetic friction, not static friction, kinetic friction. So we're using the 0.2. And we know that the Fn must equal mg, because we're on flat ground, right? So 0.2 times mg. Not just mg. That's still a sticking point. This is mass. Weight is mass times gravity. So 0.2 times 100 is... let you solve it. Sorry, I said I wasn't going to solve it. I did give you one answer there. But the base of the problem, or the key here, is that it's a steady speed, which means there's no acceleration, right? Which means that there is no net force, and these 2 things have to be equal to each other. So I can find the push force by finding the friction force. All right, so get these done, hand them in. These packets will be due tomorrow. Also, you'll have this video to go back and look at. So do turn the packets in. That's kind of your check for watching this also. Have a good day. See you tomorrow.